Hello, today we're going to talk about inverting the z-transform. The types of z-transforms that we're going to see are almost exclusively what you would get from a difference equation. In such a case, you have a fraction with a polynomial in z to the negative n on the top. The coefficients are the x coefficients or the feed-forward coefficients, and on the bottom we have a polynomial in z to the minus k with the ak's being the coefficients, and those are the feedback coefficients. So x of z can be factored. This polynomial, like any polynomial, can be factored. We'll take some gain functions out front, and it's now a product of root terms that look like 1 minus ck, and we're going to keep operating in these negative powers of z. Minus dk z to the minus 1. Okay, so this is just a factoring operation. Now, as you may know, it's easy to factor something that is second order. Third order is possible, but often difficult, and beyond that, it's very difficult to do by hand. Fortunately, in MATLAB, there's a function called roots that you can use to factor a polynomial. So if you ever get one big enough that you have to do that, then actually it turns out that you can also just use another function in MATLAB called residue z, which completes this whole operation, because our next step is going to be to do a partial fraction expansion. And this result is going to give you a bunch of z terms out front, depending on the relative orders of the numerator and denominator polynomials. And then terms like this. So the partial fraction expansion is essentially the way to invert your z-transform. Okay, so once we have our partial fraction expansion version of it, then we can take the inverse z-transform simply by doing a table lookup. So all these terms here are going to essentially now be delayed delta functions. So this would be a sum of BR delta n minus r over r, and this part will look something like that. Okay, so then we've done our partial fraction expansion and directly converted that into our time domain function via their lookup tables. So, while you can use MATLAB to do your partial fraction expansion, you should know the basic ideas. And so let's go through just a review. And this is covered also in the text. And in fact, the text goes into some details that I'm not going to, just in interest of time. In particular, if you have repeated roots, you have to treat it specially in your partial fraction expansion. So step one is if the numerator is of higher order than the denominator, then you do long division until you have a remainder that is of smaller order or equal order to the denominator up in the numerator, and you do partial fraction on that remainder. So you saw that right up above here where in the process, although it wasn't shown, some long division was done to get these BRs, and then on the remainder we did the partial fraction expansion. So the second step, factor the denominator. And the third step is, if there are no repeated roots, then you multiply the expression by each factor in turn and evaluate at that point. So what this looks like is you get 1 minus dm, whichever you decide to do, z to the minus 1 multiplied by x of z evaluated at z equals d to the m. So this is equivalent to multiplying our sum over r of our b terms, the capital B, minus r, and evaluating that at z equals dm. And since z equals dm will cause that to go to 0, this whole thing disappears. So this is the part that came from the long division. That part goes to 0. Now we also add in our partial fraction expansion. We don't know our AKs yet. That's what we're finding. We multiply this by 1 minus dm z to the negative 1, evaluated at z equals dm. So this is going to go to 0 except when m is equal to k, or k is equal to m. And the result will equal am. So step 3a, what happens if we do have repeated roots? The textbook covers this. The problem with the repeated root is when we multiply by 1 minus dm, it's not going to cancel out both of the roots, and so we'll be left with some ambiguity. So you can take a look in the textbook for that. Okay. Next, I'm going to show an example. It was one that was done in a previous year, so I'll just copy and paste the whole thing into the notes here, and then we'll go through it rather quickly, but just to show some of the key points that we've just gone through. Okay, the first thing I should say is that this, as I mentioned before, is from a previous semester, and that semester I spent more time dealing with left-handed sequences, and so this actually will yield a left-handed sequence, and that's different than what we'll be seeing this semester. However, the steps for doing this are all the same, and so it's worth going through for that reason. Okay, so we start out with x of z, and we have a polynomial in z to the negative 1 in the numerator and 1 in the denominator. and we want to invert this. So we can't do that right away. The first thing we need to do is factor it. Well, we have binomial coefficients up above, so that part's pretty easy to factor. We get 1 plus z to the negative 1, all raised to the third power, right here. And then in the denominator, we can factor that using inspection, or you can use the quadratic formula. And so we find that also, when looking at this, that we have a numerator of higher order than the denominator. So the first thing we need to do is long division. Long division, just put your two polynomials, the denominator on the left, the numerator on the right, in decreasing negative powers of z. And if you don't recall how to do polynomial division, it might come back to you by looking at this, or you could go do a quick search on Khan Academy or something like that, and they'll probably go through it much more elegantly. So when we've done our long division, we get several things here. The first is the result is going to be the b terms out front. So they come right down to here. And then we have the residual, and that goes back in the numerator. So we're getting close. Now we postulate that this can be expanded in partial fractions, and it is indeed the case. So we set up our partial fraction expansion as 0.5 z to the minus 1 plus 2.25, plus we have two terms, one for each factor in the denominator. It helps to have the entire thing factored over on the right. We could have, of course, just put it in the original form that it was given to us up above here, and that would work too, but this generally tends to be easier because now we will first multiply both sides of the equation by 1 minus z to the minus 1 and evaluate it at z is equal to 1. So that wipes out the two terms out front, and it wipes out the a2 term. The a1 term is left alone, and so we get a1 is equal to the whole function evaluated at that point. To evaluate it at that point, you notice that we had before 1 minus z to the minus 1, and that cancels out because we've multiplied the whole equation by that. Okay, so we throw a 1 there, and we get 2 to the third over 1 minus 2, and that gives us our negative 8, which is our a1, is shown right there. Next, we do the same thing, and we find that a2 is equal to 1 plus 1/2 over 1 minus 1/2, and the upper part is raised to the third power. So the result is 6.75. We now have our a1 and our a2, and x of z can be written as that. To now go backward to do our inverse z transform, that just moves straight down. 2.25 becomes 2.25 delta n. This becomes 1/2 delta n minus 1. And this is minus 8 u of n. Now this one's kind of tricky, right? Because the coefficient a here is 1, so it's 1 to the n. And we get something that strictly isn't stable. But that's okay. We can still, because we haven't done any conversion into the frequency domain, into the DTFT, the Z transform can still allow us to talk about these things, just knowing that somewhere in the background some person wiser and smarter than us perhaps is keeping track of the regions of convergence and making sure that we're okay. This particular one also has this 2, so we have our A term is now 2, so we have 6.75 2 to the n, u to the n. Well, that is definitely unstable. While u to the n just never dies out, this one blows up. As we discussed briefly when we were talking about Fourier transform pairs, if you have a situation like that, the exact same Fourier Z transform can be inverse transformed into a left-handed sequence that is stable. So these two sequences that I've highlighted here, this and this, have exactly the same Z transform with just simply a different region of convergence. As I said, we won't be worrying about that much in this class, but this is the general procedure that you follow for doing a partial fraction expansion.